Welcome everyone. In this video I will go over Newton's method and show how we can use it. To do that I am going to draw a coordinate plane here. And as you can notice I drew it very large so that you will see what is going on very clearly. Let's say that we have some arbitrary function that goes like this. Perhaps, okay? Well, actually, let me make it something else to illustrate my point more clearly. Okay, this will make it easier to draw on. Now, Newton's method is used to approximate values of the roots of a function. So maybe you want to approximate this value of the root. So you want to approximate the value of this root, right? So how can you do it? Using Newton's method, which we will derive in our discussion right now. But first, to use Newton's method, you need to take a starting point. You need to kind of make a guess to what the root is. All right, and as you can guess, the closer your guess is, the better it is. And if you make a closer guess, the Newton's method will give you the answer more easily. Perhaps you chose x naught as your starting point, and x naught corresponds to this point here. So you draw the tangent line there. You draw the tangent line, and now the point where the tangent line intersects the x-axis, the horizontal axis, you choose that point as your x1 point. Then you draw the tangent line from x1 to your graph, maybe something like this. Now this is x2. You again do the same thing, and you can see that the values that we choose are getting closer to the actual value itself. They are getting closer to the root. And when we draw the tangent line now, it is nearly the same thing as our root, right? Very, very close to it. So the basic idea here is that if we iterate this process, if we continue this process, at the end of the day, we will come to the root. We will find its value, or we will find a very good approximation for its value. So the idea is, if we think of the first approximation that we made, if we think in terms of this first line here, all right, we will now represent x1 in terms of x naught, and then we will make a generalization in terms of n and n plus 1. So let's get started. If you look at, and this is f of x, by the way, function is f of x. If you look at the slope of our first tangent line, we can see that it is equal to the derivative of our function f evaluated at point x naught, right? The derivative will give you the slope of the tangent line. So this is correct. And we know that the slope is also equal to delta y over delta x. Well, for our delta y, we will have f of x naught, right? This point corresponds to f of x naught minus, well, 0, because we are at the x point, we are on the x-axis, and then we will have x naught minus x1, right? Maybe I should highlight it in green. So this distance, right? We use them to find the slope. All right, great. So if we, and this is x1, by the way. So if we solve for x1 here, what do we get? What do we get? Well, you will get, if we multiply both sides with x naught minus x1, we get this as equal to f of x naught. So we divide both sides by the derivative, and I'm going to do it here and erase this part now. So it is gone. So if we, if we add x1 to both sides and subtract this division right here, that ratio, we will get that x1 is equal to x naught minus f of x naught divided by the derivative at point x naught. And this is actually the formula for using Newton's method. And on the next page, I will write the general formula. The general formula is for n plus 1 and for n, the relation between the two. So for finding the n plus 1 x, you simply get xn, then you subtract f of xn, so the function evaluated at point xn, and then its derivative, the derivative of the function evaluated at point x is equal to xn. This is the formula for Newton's method. As you can see, and as I talked about it, it is an iterative process. You iterate for a couple of times, for how many times you want, and you get closer and closer to the actual value of the root. So this is Newton's method. And I want to go over an example so that I will make sure you guys understand this topic, because this, up to this point, the video might have been a little theoretical, but I think an example will help you understand it a lot better. So for the example, let's say that we have a function f of x, which is equal to x squared minus 3. Now, using this function, we can find the value of square root of 3, right? We can approximate the square root of 3, and we never can find the exact value for it because it is an irrational number. But we can get closer to it. We can get a very, very accurate result. So how can we actually find an approximation for the square root of 3? Well, the first point to notice here is that the square root of 3 is a root of our function. If you plug it in the function, you get 0 as the output. So it is a 0 of our function, which means since Newton's method is used to find the zeros of a function, for example, this 0, since it is used to find zeros, we can use Newton's method on this function to find its 0, which is the square root of 3. So let's get started. We will need the derivative of our function, so let's just take the derivative. We will simply get 2x, because if we use the power rule, we bring 2 forward, then we decrease the exponent by 1, so we have 2x. So let's choose a starting point, and a good x0 value would be a value that is close to the root itself. We can tell that the square root of 3 is obviously less than the square root of 4, and it is greater than the square root of 1. So the square root of 3 is greater than 1, and it is less than 2. And it looks like it is closer to 2, right? Because, when you compare these numbers, you see that the square root of 3 is probably closer to the square root of 4. Alright, so with that in mind, let's choose our x0 as 2. Well, if our x0 is 2, we can find x1. What will x1 be? It will be, using the formula above, it will be 2 minus f of 2 and the derivative evaluated at point 2. So we have 2 minus, what is f of 2? If you plug in 2 in the definition here, you get 2 squared, which is 4 minus 3, 1, divided by 2 times 2, 4. So this is equal to, not 3, 7. divided by 4. Right, if we, let's do it with x2 as well. We now have x1, we subtract f of 7/4 and then f prime of 7/4 minus, well, let's do it like this. We square it, a minus here, and 2 times 7/4. Now you could work this, algebraically, or you could do the arithmetic, or you could just use a calculator, which I will do now. So I am going to get my calculator. All right, I use my calculator to find that this is equal to 97 divided by 56. Now we could go on and on. We could do for x3, x4, x5, but let's just write the decimal values here as well. So the decimal value of 7/4 is 1.75, and the decimal value for 97 divided by 56 will be, and I'm using my calculator again, it is 1.73214. So my claim is, the idea behind Newton's method is, these values should come closer to the square root of 3. So in a sense, when we hit x of x infinity, we should get the square root of 3. And what is the actual value of the square root of 3? Well, it is 1.732. So we are already there. And we only did 2 iterations, right? This is the first one, this is the second one. So this is a very, very effective method to find values for irrational numbers, like the square root of 3. And as a check on this topic, to really understand it, you could try to find the values of the square root of 2, square root of 5, square root of 7, square root of 11. You could do it for anything. And in the next video, I will use Newton's method to approximate the value of pi. But anyways, this is it for this video. I hope you found this video helpful. If you have any questions or suggestions, please write them in the comment section. I hope to see you in another video. Until then, take care.